Assalamualaikum. Good morning, everyone. Um, so, if you guys are to start on that, so we understand. So we are the last part of the course, last 2 days. And essentially, I want to do two things. I want to look at the important learning regime feedback, the entire section of literature in large language models, which is a fairly important one. We look at an explanation of the important learning, how the important learning works, how important learning is used for energy applications like large language models. It's a little bit mathematical, but not a lot. Okay? Just try to follow along. It's good to know a little bit of the math because, as I mentioned, the goal for me is to do that really very quickly. If you read the literature, then you really understand version of mathematical text in this way. Okay? And I also want to do the later half of tomorrow, to do like higher level course that we have done. Therefore, if there are any questions, you can check it. One last thing, so on Monday, I will share with you guys schedule of the deadlines of each homework, assignment, and exam. I have to go back and talk to the guys because we moved the end of the degree a little bit later. So I want to know when that can be, and then align all the deadlines according to that. Because, for example, we wanted to schedule the final exam in the first week of May. But I have to check that you guys have not received the degree. There's not something. Monday or Tuesday, it has to be talked to the register of office in more, so that it has been sold. Just bear with me. It's nothing to worry about because, as I mentioned, I'm very flexible with it, right? After maybe 3 or 4 days before the meeting, as long as we can break with that, but I'll give you the exact date. Before okay. One again, regarding the design, don't worry too much about it's more for my use in your use. I'm not going to ask you to do math. If any math needs to be done, I do it myself. It will be in the question. Okay. And it will be much more difficult. So no, no good. Very good to do that. It will be going to that sort of math. We expect it to be around 1 hour to 2 hours, not necessarily a lot of time. I'm not going to check memorization as much as it's going to take a bit time. Okay, but it's good. I will work in this way. So it's not going to come to the first again. Okay, any questions regarding what is the course? Okay, so I'm sorry. Yeah, the material will be what you covered. Okay, if you covered in the class, it might be a little bit of an extension of it. It's something that we discussed, but I might ask you to think a little bit more about it. For example, I might ask you to, okay, I want to write a setup where I think I've lost in the next position, but next 2 positions, for example. So this is the setup. Now, this is not what we explicitly studied in this class, but we studied in this class because we looked at the setup of one position, which is not really something. usually it's not an exam as quickly like $400 country. So don't worry about it. If you do like half of it or 30 or 40, don't worry about it. Then you design. It's hard, but like to test your understanding of it. Okay? Yeah. I will say Monday exactly. So I will create the question like a sample exam. And I'll share Monday, Tuesday, and Thursday, and I'll create the question with you. Um, so that you guys have an idea of it all. But as I mentioned, it's only going to test understand that the concept that we discovered is this. Because essentially what if I want to visualization at the time, I'm not interested in memorization, it's knowledge, the computation of data that is great, but if you understand the city, then it's easy. Okay? Any other questions? Yeah. No, that's why I'm not giving you the data right now. I will go back and I will put it out exercise option. So it would either be, for example, like I would request the next course professor to give me 1 hour of cognitive day, or I might ask the college to give me an extra day. For example, you come from Thursday to Sunday, this is like 15 days one, but because we have the relation with it, it's not going to be it. But we remember it is yeah, I remember I will need the deadline prior to the year because I want to have to but I will give you the same. Also start thinking about the project idea because towards the end of the semester I will become quite close. We can application, some application on some large language models in the world. The multiple models and the any answer. I don't know. Idea is because we have that in the field to be able to take something for this part. Okay? I will discuss the details in the year and we can discuss what is the idea. So let's deploy that into the question. Okay. So let's come to the topic of it. I have about 6 pages of derivation here. This is the data and explanation for this guys. The important learning is, I would say, the area of AI where the theory is clearly well defined compared to other areas. So for example, there is in fact mathematical theory called supervised command, which is reducing the network for the loss of the backlog. Okay? So the important learning we do set up mathematical models for the problem, and there is very good intuition with it. It has been developed over 30, 40 years of research. And I mentioned yesterday that it is in fashion these days, during the trial certain models, the course book is actually, the textbook is course book in almost all the research and then there was education. So it is making significant impact, particularly for energy. So we will see what is the reason for that impact. Okay. So let me start with the exam. Now, taking language model, large language model, algorithm that we see typically would have gone through 3 stages of training. Okay. So the first one is pre-training. So in pre-training, you have data from the internet. You take the data from the internet, your element, what do you do? What is the task of the task? This is the next operation. So you give us a data and you ask me to predict next token. So for example, I will pick an essay from Wikipedia and let's say another is football team based in Riyadh, right? Based in Riyadh. This is the sentence. So what you will do is you will add a start of sentence here. Okay, this would be the input, and then you will take the same sentence. Okay, based in Riyadh, and you will add an end of sentence. Okay, and you will do word by word prediction. So for start of sentence, you will predict another. For another, you will predict L. For L, you will predict. We are just predicting another. This is the setup that we use in filtering of the large language model. Any questions so far? Can you set this up? Thank you. To do the back propagation, we can turn the network. That's the bulk of the training of the large language model. It's stable. What about stage two? Stage two, you will see what we call supervised machine learning. Instruction fine tuning. We pick up the for example, let's say I'm going to large model in a platform. I will pick up data from high quality charts. Okay? These high quality charts can be selected, for example, when I selected the chart expression that we are going to get. Okay? Or it will be connected from customer care services. Business. So high quality data, for example, you can information like this. What is the capital of UK and capital of UK is London. So this part, it would be given as input to the sentence and it would be asked to produce the output token by token. Okay? Everybody with me? Okay. So this of course also can be done by some system block. This is the system block. Act like a useful followed by 12, followed by because that's function block that is this basically trying to get this language to behave in a way that you want. So remember in the first stage, the chatbot or the large language model is just learn the language, to learn to speak or talk in a particular language. Let's say you're just speak English. So it learns to speak English. But now you don't want it to just speak English. You want it to speak English. For example, you want it to behave like a pattern. Okay? Or you want it to behave like an assistant. Or you want it to behave like a math student, whatever it is. Second stage is for that. Okay? Again, token by token prediction, but never prompt. The prompt can be a simple prompt, query, and then start to focus on answer. Any questions so far? So, the combination of these two stages, at the end of stage two, the model would have the ability to One is it would have learned the language, learn the let's say I'm instructing chatbot. Let's say you want to do a music chatbot, math chatbot, everything. You learn these, okay? But what is missing is alignment. And what are networks to give us some information? We want it to give us some information in a particular manner. Okay? For example, if I ask it, what is the temperature of UK? If the answer temperature of UK is example, you now I would say that the certain information part in this answer is correct. That's a lot that UK is a big answer. But this part I don't want. I don't want it to be good. I just want it to be sensitive. I don't want it to be basic. This part is okay. And the question is why is this a significant part of language model? Why is this a significant problem for language? Why would the language model suffer from this classification? Because we are saying this on data from the internet. Data from the internet, the majority of it is not very well defined. Okay? It's very sensitive, very defined. Okay? So this type of, and I can show you guys what is some examples where you work with raw model, raw language model. Can be very, very, definement, the alignment, okay? The responsibility. So the person who we need to somehow get up for sure. But the thing is, as I mentioned, large language models, the performance is coming from scale. So the performance coming from scale means that you need all the data that you need. You can, of course, try to curate certain data. The people who know all the data, they will win. They will affect the model. So restricted data is not enough. You have to use all the data to you. But somehow you need to use the bad data to learn something good from that data and not learn the bad data. Because even like for example, if you a good example is like for example, using form text. You go there, there's always something bad. You try to find some let's say refined comment there. It's still English. They are discussing a topic, discussion. This is some value to that data. Because if I don't want to learn everything from this data, I want to learn the value of it. Okay? So this is where the third part comes in, which is started. Important learning is given data. Okay? And the important learning is that is actually an alignment set. Alignment set for your in this model. Okay? Now the question that you guys should ask is why am I doing it through another approach? Why can't I do it with a supervised? Okay? I have supervised learning data. Why can't I just do more of that supervised learning to fix or align the model? So the question is, the question that I'm trying to answer is that, okay, why do I need to go for this learning? I'll show you first in this paradigm. The question is, why can't I just have more supervised sampling? If it's behavior or make the model align. You can correct. You can, for example, you put questions that you get the right answer. You get correct. Okay. See, the issue is that there is a fundamental mistake with supervised learning paradigm. The supervised learning paradigm is the maximum likelihood. Give data, tell it what to do or how to make this right. So it's missing is it cannot tell that that is our possibility. There are some of that.
Interesting. Yeah, I'm assuming better, right? So the fundamental issue, well, not an issue, but design limitation of supervised learning is that supervised learning is a maximum likelihood approach. What I mean to say is that you would have some data. Okay, and you can ask your model to make this data more likely. Make data most likely. Okay. That's the fundamental paradigm of supervised learning. Now, what is the issue with this paradigm for our task? Exactly. Exactly. So what you're telling is that, hey, when somebody asks a question, how are you? Make the answer, I am good, most likely. Okay. But if you want to, for example, prevent certain bad answers, it might also be nice to push down the probability of those bad answers. Okay. So what it's saying is that Amr bil Maruf, like it's just telling it, do this thing, but it's not doing the other half. Is it's not stopping it from doing the bad things. Okay, in an ideal world, if you have massive amount of supervised data, you can get the same alignment behavior. Okay, but you would have to have huge amount of data. So think of it like you want to go to the set of all the good things and specify each one of them and tell the network just do this. Okay, that's one approach of aligning the model. Reinforcement learning takes a slightly different approach. It says we don't need to, for example, look at all the samples of good behavior. What we can do is we can look at some very likely samples of good behavior and some very likely samples of bad behavior. And then tell the network to push down the bad behavior and push up the good behavior. Okay. That's the fundamental paradigm difference between reinforcement learning and supervised learning or machine learning for that matter. Everybody's with me? Can I get some yeses on that? This is certainly going to be a question on the exam. Okay. So there's a fundamental paradigm difference in how we do learning, in supervised machine learning and reinforcement learning. The supervised machine learning is telling you what to do. Okay, it's telling you, it's giving you a data and it says make this data more likely. So you do maximum likelihood. You take this data, make it more likely. But reinforcement learning is doing is it's giving you some data which it says is good. You want to make it more likely, but it's also giving you some data which it says is bad and make it less likely. Okay, so reinforcement learning goes to specific bad cases and try to plug. Okay, so for example, an example of this would be, let's say you are in a ship, okay, and there is a leak somewhere. Okay, and you are the engineer in charge, and you tell the guys, hey, fix the entire ship. Okay, fix the entire ship, make sure that there is no leak everywhere. This is the supervised engineering approach. You're fixing the entire, you just want to do everything good. The reinforcement learning approach is you tell the guys like, hey, let's look exactly where the leak is and let's plug that. Let's go exactly where the problem is and let's solve that problem. Okay. That's the theoretical implication of the two areas. Now, let me explain what reinforcement learning is. How do we set the problem up? So machine learning, we have done a classical breakdown of it, which is unsupervised ML, and then we have done supervised ML. Up till very recently, most of the very successful application of machine learning was supervised ML application, but now Gen AI is making significant impact in unsupervised machine learning as well. But the fundamental paradigm of learning in both these scenarios is that you have to have some data. Okay, and you're going to work with the likelihood of this data, make it more likely. Okay, we have another area of AI, machine learning as well, but AI, which is reinforcement learning, where you don't have access to the data. You have access to the world. You have access to the environment. Let me explain this. So imagine you want to train an algorithm to play chess. Okay. Chess playing machine. Okay. You have set up an architecture for this algorithm. Okay, it's a deep neural network. Now you need to train it. Okay, so I can give you two approaches. I can say that a chess game is basically a series of moves. Okay, so for example, player one, queen to c4. Okay, player two, king to, I don't know, d3. I'm bad at chess and so on. Okay, this is a full game. And let's say this player one won this game. So I'd label it as 1. Okay, then I give it another game. Player one, let's say knight to e5 and so on. All the moves in the game, and I say that player two won this game. Okay, or computer won this game. This is player one. This is player two. So I can label the games like this. Now this is a supervised learning problem, right? You have some data and you have some output. You can set up a loss function, you can train it, and you can train it such that the probability of player one winnings become high. So now this, when you give it a certain state of chessboard, you tell it that these are the moves that are made on this chessboard. It will tell you, make this move. This move is going to make the probability of winning more likely. You can train a chess playing game like this. What do you think is this a good approach? Yeah, what would be a better approach? Okay. So what Shah is saying is that a better approach would be to not give it a sequential sequence of moves, just give it access to the board. let it see the board, and let it decide what the next move is. This is basically the paradigm of reinforcement learning. So in reinforcement learning, we don't generate the data about the process. We give an agent, an algorithm, access to the world where this data is coming from. So what I will do is, I will have a chessboard. Of course, along with all the rules of chess, I will give an agent access to this. Okay. Agent in our case is a learning algorithm. Okay. So this is the learning algorithm. This chessboard and its rule, this is the environment. Now this agent can decide to move certain moves on this chessboard. Yeah, for example, move a piece, move piece a certain way, move another piece a certain way. These are called actions. And based on this action, the agent can win the game or lose the game, or even be in a better position to win a game or be in a worse position to win a game. This signal is called a reward. Okay, that's the reinforcement learning setup. The reinforcement learning setup is you have an agent, which is the learning algorithm. You have an environment. Environment is the world where you want to do a certain task. It can be a chess game. It can be ability to write an essay. It can be the ability to fly a plane. It can be the ability to invest in a stock market, whatever it is. Okay, this is agent. Okay, environment is the world that the agent is working in. Okay, whatever task that it's trying to solve. Actions is the things, the different options that are available for the agent to do. For example, in chess, agent can move pieces. Of course, it cannot move pieces independently. There are some rules that it has to follow. Okay. For robotics, the agent might be able to control certain motors on the robots. For stock market, the agent might be able to buy or sell stocks. Okay. These are actions. And reward is essentially reward, the way we understand reward. Okay. When you win, when you get money, when you reach your target, and so on. These are rewards. Everybody's with me? All good? Okay. So now, okay, we have a new paradigm of learning, okay, which is reinforcement learning. We have an agent. Okay, agent can take actions. Okay, you have an environment. Environment is the physical world the agent is acting on. You have actions. These are actions that agent can perform. And you have rewards, which is basically rewards the agent receives. I'm sorry? Yeah, I'll explain what state is. Okay. So this is the general setup of reinforcement learning. Okay. Now I have a question for you. Let's say we are playing the game of chess. Okay. And let's say you currently a piece of the opponent is checking your king. Okay. So I'm hoping that you guys would agree with me that the only actions that you can do is to save the king. Either move the king or you cover the path of the attack to the king. Okay. Similarly, let's say you have an agent which is flying a drone. Okay, and the drone is very close to the ground. Okay. Now the action that you have to take is to move the drone up. Okay. So what I'm trying to tell you is that the actions that you take, it would depend on how you are interacting with the environment or where you are in the environment. Okay, this is called the state of an agent. What is the current state of the world? Okay, so environment is measured in state. State defines, for example, what is the configuration of the chessboard? How does the chessboard currently look? This is the state. Everybody is with me? Okay, and then your action would depend on this state. Okay? Because if you are a smart chess player, you're not moving the pieces randomly. You're looking at the chessboard, you're trying to see what is the current state of your chessboard, and then you're making some actions to maximize the reward. Okay, everybody's with me? Do you understand what states is? Okay, so let me look at a few things. So first, let's define state. So can somebody tell me what state is? Yeah, the current situation of agent with respect to the environment. How is the agent located in the environment? This is the state of the agent. Okay. So remember in the drone case, I said whether it's very close to the ground, whether it's at optimum height, whether it's close to the target, this would be the state of the agent. Okay. Second, we already know actions and so on. There is one more thing which I want to define, which is dynamics. Okay. Or state dynamics. Okay. So if you are in a current state and you perform an action, most likely this will change your state. So imagine you are a drone which is very close to the ground, okay, and you performed an action of moving up. So now when you perform the moving of action up, it changed your state, right? Previously you were very close to the ground, now you are slightly up. Now you are at this state, again your action is move up, so your state is changing. When you are in a current state and you perform an action, you will get a new state. Okay, this is called dynamics. Okay, and typically we say that these dynamics are probabilistic. Okay, why probabilistic? Because see, if you are, let's take the example of a drone. Let's say you are at height 1 from the ground and you say that, okay, you need to go up. So you say, let's make the velocity, upward velocity 1 meter per second. So in 1 second, ideally speaking, you should be at 2 meters per second now. But it might be that the situation is very windy. Okay. And rather than coming to 2, you come to 1.8. Okay. It might be that the situation is very windy and the thrusts are up. So maybe rather than coming at 2, you come at 2.2. So you have a probabilistic distribution on the next state. It's not fixed. From a state, when you take an action, the next state is not fixed. It can be probabilistic. Okay. In the context of chess game, so think of it like this, like you are in a state, you made a move, but then the move that the player 2 will make, you don't know it exactly. You will have some understanding like, okay, most likely these are the possible moves that the player 2 can make. So I will consider player 2 as part of the environment. Okay. So I'm agent 1, I'm agent, the chessboard, its rules, and player 2, this is environment. So I made a move, I moved the bishop. Now I don't know exactly what the player 2 would do, but I can learn, like on average, this is how player 2 plays, and it might do these moves. So you have a probabilistic distribution on the next step. These are called dynamics. Okay. And lastly, the actions that we take, we say that they come from a policy. Okay. So policy is basically a strategy which defines which action you should take in which state. So for example, this decision of moving up when you are very close to the ground, this is your policy. The policy is not to let the drone hit the ground. So when you are close to the ground, go up. Okay. You also might have a policy of not going too far up So if the drone is above a certain height, keep the height or go down. This is called policy. Okay. So let me briefly write policy as a function. So policy is, it will take a state and map it into an action. So it takes states and give you output actions. Okay. So now if you look at it, this is essentially a function, right? Okay. And in machine learning, what is the thing that we can do fairly well? We can learn functions. Okay. So essentially, the entire job in reinforcement learning for you would be to learn policies. Learn policies which tell you which actions to take in which states. Okay. And by the way, what are we doing with this? What is the desired result of learning a policy? What do we want to do with these policies? More reward. We want to maximize the reward. So you see now, this is the paradigm change that I was mentioning. So in supervised machine learning, you had some data that you wanted to make more likely. Okay. Here, you will have some data and the corresponding reward. You would say that the data for which reward is high, make it more likely. The data for which reward is low, make it less likely. Okay. That's the fundamental difference. Again, in supervised machine learning, we were using deep neural network to learn a mapping from input to output. Here we are also learning a mapping. So this policy would be parameterized by some theta. Okay. We would learn a mapping of states into action. So at which state, which actions to take. But actions, we are taking it with the goal of maximizing the reward. Everybody's with me? Is this clear? Any question? Yeah.
All policy has to be led is there fixed or
There can be fixed policies, but in general, the problem that we are trying to solve can be deep learning and machine learning. Policies are very difficult to learn. It's very difficult to fix to write a fixed policy. For example, if a robot is working in a very restrictive environment, and its task is, let's say, to pick up some stuff from here and drop it there, you can have a fixed policy for it. You can say that, okay, at every time step, if you have picked the item, just go in the direction of the target. Okay. At any time step, if you have not picked an item, go in the direction of the location of the item. If you have reached the location of the item, pick up the item. Now, this is a fixed policy. Okay. But the applications that we are interested in, particularly language model, it's impossible to write a fixed policy. You would have to learn the policy. Yeah. So essentially, what we have now is that if you have an agent, which is trying to optimize a policy, okay, you have access to an environment, and you have a reward signal coming back from this environment, you can find or optimize the policies, the actions that you take. Okay, so let me start with a small example. So let's say this is a toy example. It's typically the first example that we use in reinforcement learning course. It's called the grid world example. Okay, and the reward model is like this. Okay, if you move from this, by the way, is a reward model for CAT. So CAT is trying to learn a policy. Okay, and the rewards it's getting is like this. If you move to an empty cell, you get no reward. Okay, if you move to a broom, you get a reward of -1. Okay, if you move to a reward of a bathtub, you get a reward of -10. Okay, but if you move to the reward the cell of meat, you get a reward of 100. So now what I want you to do is to tell me a policy, the optimum policy for it. from this cell, where should the cat move? Down. From this cell, where should the cat move? Right or down? Both are fine. Okay. From this cell, where should the cat move? Right or down? Both are fine. Okay. For this, where should the cat move? Down. No, only down, because route would be a longer path. Okay. So I'll explain. I have to add discounting here as well. No, no, just bear with me. Yeah, you guys are right. Right and down are same. You guys are right. So from here it's down there. Okay. From here it's here. Then from here it's here. From here it's here. And from here it's here. Similarly. Okay. Or alternatively, you can come here like this and so on. So for each state, now I'm giving you an action. Okay. This is a policy. So now if I tell you from here, where should I go? You will tell me the best option is to go down. Right? So you guys are now giving me a policy. So you guys are giving me an action for each state. Okay, everybody's with me? In this case, how do we represent a state? State is a location in a 2D grid. So for example, this state is 1, 1. This state is 1, 2. It's just a representation for the state. This state is 1, 5. This state is 5, 5. Okay. So now based on the environments, I had the dynamics of the world as well, right? I knew that if I take a step in this direction, I will go here. You can have, of course, probabilistic models as well. Let's say that this is a kitchen floor and the floor is wet. So with 80% of probability, you go in the direction where you are going. 20% probability, you slip in a random direction. You can also have this case. Then your dynamics would be probabilistic. Your next state, given a state and an action, would be probabilistic. Okay, but that's basically the setup. That's the setup that we are trying to solve in reinforcement learning. Okay, everybody's with me? Okay, so essentially, if you have access to an environment and you have a reward signal, you can, theoretically speaking, find policies to minimize that reward. Okay, any questions so far? Yeah. Let me talk a little bit about discounting, because I used discounting, but I did not mention it explicitly. If I give you two trajectories is basically the two ways of interacting with the environment. If I tell you that you have one policy where in time step 1, in a single step, you would get a reward of 100 and you will stop. Okay. Let's say it's an investment strategy. You can like buy something. Tomorrow you will get $100 and that's it. They will give you your money and the return. Say stop, khalas. Okay. Another thing is at time 2, you will get a reward of 100 and then the investment strategy would stop. Let's say it's a bank. You go to a Raji and they say, give us $100. Tomorrow we'll give you $200 and your $100 and 100 additional will stop. You have this option, or they tell you that give us $100 and after 1 year, we'll give you $200 and we'll stop. Which one will you take? The first one, right? Because in general, we want the reward to be near to us in time. Okay. We don't want a reward in future. We want a reward right now. Okay. This is actually one of the bigger problems with human behavior, is that our behavior is very tailored toward optimizing the short-term gains. So we just want to relax now, enjoy now, play now. Don't look at the long-term horizon. Okay. So how do we write this in our algorithms? How do we write this in our algorithm? How do we ensure that we keep track of a reward immediately weighted higher than a reward in the future? So the total reward essentially would be from time t equal to 0 to infinity. Let's say it's an infinite horizon problem. Okay. And the sum of rewards that you are getting at this time. So you're adding reward at time 0, reward at time 1, reward at time 2, reward at time 3, reward at time infinity. But as I mentioned, reward close to me, I want to weight it more. Reward further away in the future, I want to weight it less. So what I will typically do is I'll put beta to the power t, where beta is a number, it's typically like something like 0.9. Okay, so if you give me $1 today, to me, its value would be $1. If you give me $1 tomorrow, its value for me would be 0.9. If you give me $1 the day after, its value for me would be 0.81, and so on. Okay, so this discounting is universally added to reinforcement learning reward maximization objectives. There is another advantage to it as well. Okay, the other advantage to it is that if you look at this, let's say beta is equal to, let me remove beta. The rewards typically would be positive numbers. Can be negative as well, but typically it would be positive numbers. Can you tell me a problem if I want to maximize this? Maximize, let's say, this function. Can you tell me a possible problem with this? What can be an issue? If I want to maximize this objective, what is a possible issue that you can foresee? If it's an infinite horizon problem, this can be infinite. Okay, you have sum of positive numbers. This can become infinite. Okay, but if you put a discount factor, beta to the power t, okay, and let's say I tell you that the maximum value of R is 1, then I can put an upper bound on this. This would be bounded. Okay, so beta allows us to bound return on infinite time intervals. This thing equal to 0 to infinity, beta t. This is called a return. So return is basically the summation of rewards at each time step, adding them together. If there is a discount factor involved, with the discount factor, and that's it. Everybody's with me? Yeah, it's typically 0.9. Typically, you can, it would be between 0 and 1, of course, because you're doing discounting, right? So it should be between 0 and 1, 0 and 1 not included, right? Yes, this beta will ensure that reward in near future is weighted more than reward in the future. So let's look at a simple case. Let's say that my return is equal to 0 to infinity, beta t, and reward. Let's say I take an example. I say that at t equal to 10, I get a reward of 1, and the simulation terminates. Okay, the scheme that I'm in, it terminates. All the other rewards are 0, by the way. Okay, so what would be the G? G would be 0.9 to the power 10, right? Now let's say I get at time equal to 1, a reward of 1, and the process terminates. So what would be the return? G would be summation t equal to 0 to infinity, beta t on. This would be 0.9 to the power 1. Same reward, right? But closer to us, it's weighted more. Away from us in the future, it's weighted less. Okay. So now in general, I'm hoping that we are on the same page in terms of the setup for the reinforcement learning problem. So in reinforcement learning problem, I would typically have a policy network, okay, that would take in a state and it would tell me what actions to take in this state. Okay. what is the goal? What is policy network trying to do? It's trying to maximize the reward. So now let me explain why we are doing it. Yes.
Well, the reward have to be the same. So, the reward in the future, we could,
Of course, yeah. So if reward in the future is very big, with even with the discounting factor, of course we'll go for it. So think of it like this: like if I tell you that you can sleep in the class today, you will have a reward of 1 because you will enjoy for 1 hour, or you can work hard today and 2 months down the line in the exam, you will do a good exam and then you will have it for the rest of your life.
that's the dream.
Yeah, it's not great. It depends on the quantity of it. So of course, it's better to stay awake in the class and do a good exam and then be happy for the rest of your life then. Because the magnitude of the rewards are different. Okay. So now the question is, the $1 million question is, why am I discussing all of this in an NLP class? Okay. What does this have to do for me? In large language models, why is this important? So in large language models, this is important. Imagine that you have a policy network where the state is the current state of a sentence. Okay. So let's say the state is, what is the capital of UK? This is the state. And now I ask it to produce the next token. Action is prediction of the next token. Give me a distribution on the next token. And it produce 2 set of next token. Okay. It produce in one step London. In the other step, it produce chocolate. Okay. Which one of these 2 do you think would have a higher reward? London. So now you can see that you have this. If it was a supervised learning problem, you would have this in your data and you would make it more likely. But in this case, I would make it more likely and I would make chocolate less likely because I have rewards for them. Okay. So the reward for this would be maybe 10. The reward for this would be maybe 0. Okay. But what is the rest? But how would you make it unlikely? Remember, the tool that we have in machine learning is maximum likelihood, right? So do you have a mechanism? I can tell a deep neural network to make this data likely. Do you have a mechanism to tell a neural network to make this data less likely? I got it. Yes, I got it. But how? How will you tell it not to make it less likely? Here in this setup, because we'll have a number, a reward. So you see, maximum likelihood is essentially this, like you have log likelihood of action given state, right? This is what we do in machine learning. We maximize it for theta, given the data that you have. Okay. What I will do is I will say, don't do this. Weight it by the reward. So if the reward is high, this quantity would be more important. It will make it more high. If the reward is low, this quantity would be less important. It will make it small. Of course, you have every right to say that, Naeem, if I'm making London more likely, I have a probability distribution. Of course, I'm making other things less likely. It's a probability distribution. If you train your network to give 100% probability to London, it would give 0 probability to chocolate. But as I'm saying, the issue with this approach is that you are trying to solve a problem without explicitly knowing what the problem is. You know the right answer. You don't know what are the wrong answers that people typically give. The good thing with reinforcement learning is that it also gives you the wrong answer. So you can go specifically to that part of your distribution and fix it. So think of it like having a hole in the board. You can, of course, say that I will put a new metal surface on the entire board. It would fix the hole, but it would be too much work. You can go specifically to the point where there is a problem, plug that hole, and fix the problem. That's what reinforcement learning allows us to do. Okay? Yeah, let's go pray. Let's come back and then we'll see how we set it up mathematically. We've already motivated it. This is essentially the key idea. Okay, weighted maximum likelihood, but let's try to set it up. Right. Right.
So
Assalamu alaikum. Shabab. Assalamu alaikum, guys. Let's settle down. Mic testing, mic testing. Okay. Okay, guys, let's settle down, please. Thank you. Okay, guys, so let's start. Okay, so we have set up the problem of aligning a language model as a reinforcement learning problem, very roughly. Okay, the idea is that the language model would be a policy network which would define which next token to produce. And of course, we will have a reward for that next token. And we will try to maximize the cumulative rewards. Okay, maximizing the cumulative reward would imply that the trajectories or the sentences or the answers which have high reward will push them up, will push their probability up. And the answers which have low reward will push their probability down. Okay, now let's write the formulation for it and let's try to see how it's done in practice. Okay, so there are multiple reinforcement learning techniques. The techniques which are used for model alignment in large language models, these belong to the class of policy gradient methods. Roughly speaking, if you have a policy network which is giving you an action given a state, my goal is to find a gradient of this policy network with respect to theta, and then take a step in the gradient ascent direction such that the overall return increases. Okay, so let me repeat it again. If you have a policy network which is giving you an action for each state, my goal is to write the gain, okay, the total reward for trajectories using this policy network. Then take a gradient with respect to parameters of this policy network and take a step in the ascent direction such that the OLR return increases. Okay, so first, let me write return mathematically. Let me write the expectation of the return and then try to optimize it. Okay. So first thing that I want to talk about is something called a trajectory in reinforcement learning. So reinforcement learning essentially is you will be in a state, you will take some action, you will go to a next state, you will take some next action and so on. This state action collection is called a trajectory. So for example, let's say you are at state 0, you took an action A0, you came to state S1, you took an action A1, you came to a state S2, and so on. All the way till state T minus 1, you will take an action at T minus 1 and you will reach SD, which is typically called a terminal state. Okay, what would be the terminal state in the context of large language model? End of sentence. Okay, end of sentence token would mean that you are at end of your trajectory. Now, when you are at state 0 and you take an action 0, you will get a return. You have the choice of writing the return either as return at time 0 or return at time 1. In most reinforcement learning books, it's assumed that if you are at state 0 and you take an action 0, the return will come at time 1. Okay, so you will have reward at time 1, reward at time 2, reward at time 3, and reward at time t. I might, when I'm speaking, I might mix reward and return. Reward is for one time step. Return is the sum for all time steps. Okay. So let me write it like this. This is reward, and return, I will write it with G. Okay. So what would happen is that if you have a policy network, okay, remember that action are probabilistic. Okay, you will get a distribution on next token. You don't get one next token. Okay, similarly, the next state can also be probabilistic in general. Okay, so you can have different trajectories. You can have a different sequence of S0, A0, S1, A1, and so on. Each one of these is called a trajectory. Okay, so this network would induce different trajectories. These trajectories I would denote it by tau. So tau is essentially S0, A0, S1, A1, all the way till ST. This is called a trajectory. Okay. Everybody's with me? Any question, any confusion with the notation? Somebody has to say yes. Otherwise, I'll ask the question again. Okay. Okay. Now let me write the return. Okay. Return, as I mentioned, return for a trajectory tau would essentially just be summation from I equal to 1 to t, beta to the power I minus 1, return a reward at time t. Okay, so I'm adding all of these, R1, R2, R3, all the way till RT, I'm adding them up. Okay, this is the return for a trajectory. Okay, now if I ask you, what is the expected return for a policy network? Can you guys write it for me? You have a policy network. This is giving different trajectories, right? So this is giving different trajectories. For each trajectory, you have a return. I'm asking you to give me the expected return. Okay, let me simplify the problem a little bit. Let's say that I tell you that I have X coming from a distribution. Okay, and I tell you, give me the expected value of f of X. What would that be? Yeah, but how will you calculate it? What is the expression for it? Okay, so it's basically, as Muhammad mentioned, it's essentially a weighted mean. Okay, what you will do is, first you will see how likely each X is. Each X is likely because it's coming from a probability distribution Px. If you want to see how likely it is, you'll just go to the distribution and see how much probability is assigned to this X. Okay, next, you will multiply it with f of X, and you would just take the integral for X. This is the expected value of f of X such that X comes from Px. Okay, that's how we calculate it. Now, of course, in practice, in computation, what we do is you just sample some X's, okay, and you will, for example, have summation from I equal to 1 to n, f of xi divided by n. Yeah, so you do some sampling and you get basically, this is called a sample mean. How are these two equal? Remember here, I'm weighting each X with this probability. If you are sampling from this distribution, of course, the X which has high probability, you will have more samples of those. X which has low probability, you'll have lesser number of samples of those. So essentially, this is expectation. Right? An important concept, by the way, to know. Okay. So now I'm asking you guys, what is the expected return If I give you a policy network, can you guys give me the expected return for that policy? Yeah, it's the mean for return. So you will take return for a trajectory, okay, and you will multiply it with how likely that trajectory is. Okay. This probability distribution is parameterized indirectly by theta because it's coming from the policy network. Okay. And you will, of course, integrate it for all trajectories. This is the expected return. Okay, you might see it written like this: station of trajectories induced by the policy network, theta. So both of these are equivalent. Okay. Now, if I give you the expected returns and I ask you, how would you modify the theta such that the expected returns increase? What would you do? So what I want to do is I want to make changes to theta such that this quantity, integral P of tau, G tau, D tau, this increases. Because remember, I'm doing reinforcement learning. My goal is to maximize the return. So how would I do it? We have taken, of course, some probability, right? Probability statistics. Okay, then we should be able to answer this. So simple thing. If I give you a function f of x, okay, and I tell you I want to change x, okay, such that the value of the function increases, what will I do? I'll take the gradient and I'll take a step in the same direction. Simple thing, nothing too fancy. Okay. So let me try to take the gradient with respect to theta. So if I take the gradient of the expected return, this would be the gradient with respect to theta. Okay. If I have this quantity, then I'm set. I'll just take steps in the ascent direction. Okay. Let me do some simplification steps and see if you guys agree with me or not. Can I take the gradient inside the integral? Can I do that? Why? Because derivatives are distributive over sum. Okay. If you have derivative of sums, it would be sums of derivatives. Okay. So you can take derivative inside a sum. Now the question is, can you calculate this quantity? Can you guys give me this value? Because if you can give me this value, then I can just simply take a step in the ascent direction and I'm set. No, but it's not an integration over probability, right? It's integration over gradient of a probability with certain variables multiplied by g tau added over all the trajectories. So essentially what it means is that you will go to your policy network, you will sample all trajectories, you will get all trajectories, okay? You will calculate the gradient of each trajectory with respect to theta and you will add them up. Okay, this is a difficult quantity to find out. At least I don't know how to do it. There is, however, something which we have used universally in machine learning. In fact, we do it every time, which is this thing. Whenever you have an expectation of a function from some distribution, what you do is, rather than calculating this expectation, you take certain samples and you take the sample mean. This we can do. Okay? So this, I should not write it as exact equality. This is approximately equal to. If you have very large samples, then it would become closer and closer. The expectation would be closer to the sample mean if the sample size is very large. Okay, so the question is, why can't I do this thing here? Because this is not an expectation. Okay, this is not an expectation. It's not multiplied with probability of theta. You're not taking integral over probability of theta times some quantity. Okay? You're taking integral of gradient of probability times some quantity. So you cannot approximate it with sample mean. So now the first trick that I will do is, to make my life easy, I need to come up with a way of converting it into an expectation. If I can convert it into an expectation, then I can approximate it with sample mean, which means that I will take just a few trajectories, calculate the quantity over the few trajectories, take the mean, and that's it. Everybody's with me? So can you guys tell me how I can convert this into an expectation? Okay, so I'll give you guys a trick, which you should keep with you for eternity. Whenever you have gradients of probabilities, you can very easily convert them into expectations. How? So what I would suggest we do is rather than taking the gradient of the probability, rather than calculating this quantity, which is tricky, which at least I don't know how to calculate in an easy, tractable manner, what I will do is I will ask you guys to calculate the gradient of log of probability. Okay. Let me calculate this gradient. Okay. Can you guys tell me what this gradient would be? 1 over theta tau, and then gradient of theta tau. This is the thing which I cannot calculate. Okay. Is it okay if I take this there? Okay. Let me do that. This will become p theta tau, gradient of log of p theta tau is equal to. So now you see this thing I could not calculate, but this thing is equal to this. Is it okay if I replace this in the equation there? Right? I can replace it. It's exact equality. So what I'm saying is that I'm going to take gradient of probability of theta and replace it with this value that I have calculated here in, let me call it equation A. Yeah. Let me make the substitution. So if I make the substitution, now my expected return was gradient theta tau, g of tau, theta, which I could not calculate. Now, if I make this substitution here, this would become p theta tau, gradient of log of p theta tau, g tau, theta. Now, can you see the value of doing this? Can you see why it's a good idea? Muhammad Rashid, why this is a good idea? What is this quantity now? So you see we have a probability here, right? We have a probability here, which means that this is expected value of this quantity. Remember, I wanted to write it as an expectation because expectation I can always approximate with sample mean. So I can take a few trajectories, take the mean of the quantity, and that's it. So now this, I can write it as expectation of trajectories reduced by the policy network, the gradient of the log of theta tau, g tau, theta. Okay, this I can do. It's not terribly difficult. Okay, I can calculate it somehow. Okay. Any questions so far? Now we can sample because you have an expectation, right? So you just take a few trajectories, take the log of the probability of that trajectory, take the gradient of it, okay, and we are set. Multiply it with the return on that trajectory, and you're good to go. Okay. Let me do one more simplification step, which is, let me write what is the probability of a trajectory. How likely is for us to observe a trajectory? Okay. So remember, a trajectory, we wrote it as you are in a state, you take an action, come to a next state, you take an action, take a next state, take an action, come to a next state, all the way till st minus 1, take an action, come to st. Okay. So this is a trajectory. Okay, this is a tau. If I want to write a probability of this trajectory, this would be equal to the probability of the starting state. What is the probability of ending up in a state? Okay, times what is the probability of taking an action is 0, given in, so we have, by the way, we have a policy network, which you give it a state and it gives you probability of an action. Okay. And you have the dynamics. Probability of st plus 1 given st and at. Okay, so what is the probability of taking an action a0 while you are in state s0? This would be given by your policy network. Okay, then if you are in state s0, you take an action 0. What is the probability of landing in state s1? This would be given by your dynamics. Okay, so the probability of s2 given, sorry, s1 given s0 and a0. Then what is the probability of taking a1 when you are in s1? This is pi a1 given s1. Then what is the probability of reaching s2 given you are in s1 and you take action a1? Yeah, this would be s2 given s1 and a1, and so on. Everybody's with me? I'm just writing out the probability of a trajectory. And the probability of a trajectory is the probability of each of the component of it, the product of the probability of each of the component. Starting from S0, what is the probability of taking an action A0 times what is the probability of reaching S1 given S0 and A0, and so on. I have explicitly written out the full trajectory probability. Okay. Next, if you guys allow me, I can simplify it a little bit. I can write it probability of S0, okay, from time equal to 0 to t minus 1, okay, probability of at given st times probability of s of t plus 1 given st and at. Okay. This is the explicit probability of a trajectory. Everybody is with me? Any questions? You guys are very quiet today. If something is not clear, we can repeat it again. It's fine. All good? Morocco, yes? Yeah. Okay. So now I have a probability of a trajectory. Is it okay if I replace it in our expression? Let me call this B. Is it okay if I replace B here? Yes, I can. Yeah, remember, I calculated the probability of a trajectory. Now I'll just replace it in this expression. So if I do that, remember the gradient of my expected return was expectation of trajectories induced by the policy network log of probability of tau return on the trajectory d tau. Okay. Let me put the probability value here that I just calculated. So this would be equal to expectation trajectory induced by the policy network log of probability of state 0 times product t equal to 0 to capital T minus 1 action t, probability of action t given st, probability of state st plus 1 given ur and st, and you perform an action at. Okay, this is the probability of trajectory multiplied with g tau, and you don't need this, of course, because you have an expectation. Okay. When you have an integral, you write d tau to denote that this integral is with respect to tau. But when you have written the expectation, you can remove this out. Yes, they're built on top of this, yes. A slight modification of this, but so the first, let me just give you a brief outline of what we'll do. The first algorithm that I would reach out to is reinforce, okay, which was used in Gemini. Okay, then I will reach to actor critic, okay, which is used in several papers. Then I'll reach to PPO, okay, which was used in GPT models. Then I will do DPO, which is a very smart modification of PPO, or reinforcement learning with human feedback, and allows us to do reinforcement learning with human feedback in a smart manner. Then we will come to GRPO, group relative policy optimization, which is used in DeepSeek. Okay, but we'll look at the evolutionary journey of the field. By the way, this is very simple. If you wrap your head around it once, it literally takes 30 minutes. So yesterday I just took 30 minutes to review the whole content. Okay, last time I did a reinforcement learning course was last summer. But because you understand it once, it becomes like kind of like a hidden state of your memory, and you can very quickly review it. So don't be scared of it. Like, it's simple things. Just like you say, like, hey, I don't understand this step. Can you explain it? Because it's literally like 3 pages of math, and all of it is something that you already know. It's independence, it's expectations, it's a little bit of calculus and a little bit of optimization. So wherever you have, don't think of it as something very difficult that you will not understand. Something that you can definitely understand, just ask questions. Okay. So of course we have the gradient here. You guys should correct me if I'm making a mistake. So what is the good thing about log of products? Log of products can become sum of logs. So trajectories induced by policy network, gradient of log of probability of the initial state plus summation t equal to 0 to t minus 1 log of the policy network plus summation t equal to 0 to t minus 1 log of the dynamics times the return on the trajectory. So now I have a question for you. Can your large language model change the probabilities of questions that a user will answer? I'm sorry. Can your large language model affect the question that a person will ask, will ask? No. Okay, the initial state, the question, the information that a user asks, it's not controlled by the policy network. It's not controlled by the large language model. So this gradient would be 0. Remember, gradient would be 0. The quantity is not 0. Okay, but I'm using a shorthand. Similarly, can your policy network change the dynamics? Let's say you are in a drone, okay, and you decide to take an action. Can the drone change the world that you are living in? No, dynamics are not affected by policy network. So this thing, this quantity cannot be changed by your policy network. Okay, so this thing simplifies to expectation over trajectories introduced by your policy network. Summation t equal to 0 to t minus 1. Again, I'll take the gradient inside the summation because of the distributed property of the gradient. Log of at given xt times theta. Okay. And that's it. That's the first checkpoint that I want to achieve or reach. Yeah, but if you look at it in a little bit of okay. So in order to optimize my expected return, I have to take the gradient of this quantity and take a step in the ascent direction. Okay, what I'm going to do is I'm going to write on the side supervised learning expression, maximum likelihood, and I will write the gradient ascent for maximum likelihood as well. And then we see if we can make a connection between the two. So without going into too much details, so this is, I will call it policy gradient. Ascent step. This is the gradient direction. This is the direction in which if you make a change of theta, your return would increase. Now let's look at the maximum likelihood expression. So the maximum likelihood expression, let me write it in a different color. So it would be summation. Let me do it for large language models. Okay, so from I equal to 1 to n, you have n pieces of text. Okay, then you have summation j equal to 1 to let's say what is the term that we use for context length? Let me call it m, sentence length. Okay, so this would be log of probability of x ij given xi j minus 1 all the way till xi 1. Okay, this is the likelihood of observing some data in supervised learning case. This is data. Okay. Do you guys agree with me on this, by the way? Because we derived it like 5-6 times over the past 6. Of course. Let me take red. So you have some data, and I'm doing supervised machine learning. Okay. The objective of supervised machine learning is to write likelihood and then maximize that likelihood. So let me write the likelihood. Let's say you have I equal to 1, I equal to, these are different sentences. You have I equal to n sentences. Okay. And then all of these are of length m. Okay. M can be different for different sentences. For one sentence, m can be 1, for another, m can be 2, and so on. Okay. More precisely, I should write it as mi. Okay. So then the likelihood of observing this data would be, in fact, the log likelihood of observing this data would be, let me write log likelihood of observing this data, would be summation from I equal to 1 to n, summation j equal to 1 to mi, okay, log of probability of observing the JL's token, given that you have observed j minus 1 till the first token. This is log likelihood of observing your data. If you want to maximize the log likelihood, you will of course take the gradient of this. So gradient of log likelihood, let's say this is parameterized by theta as well, would be this quantity. Okay, so this is gradient of the log likelihood. Again, we want to maximize the log likelihood, so we'll take an ascent step. And this is the gradient of the policy gradient, and we are taking an ascent step on this. What is the difference in these two? The return. So you see, this is exactly the same expression, except that you have a g of a return multiplied to it. So what it means is that if, let's say for a quantity, what log likelihood is doing is that it's maximizing all the data that it has seen. It's maximizing the probability of observing all the data. What policy gradient is doing is it's taking the gradient of observing the data, but then it's multiplying it with its reward. Okay, so imagine that reward is +1 and -1. Okay, so it observed the data, it saw that the reward is +1, it would make its likelihood high. It would make this data more likely. But if the reward was -1, it would make this data less likely. So now you see the strength of reinforcement learning. Okay, so we did some annoying math, but at the very end, we have some very simplified expression. Okay, so policy gradient gives you a modification of log likelihood expression, okay, where essentially each trajectory, each data is weighted by what is the reward or return on that data. If the return on that data is high, you will make it more likely. If the return on that data is low, you'll make it less likely. That's it. That's the entire point of all reinforcement learning with human feedback that we do. Okay. I'm hoping this point is clear. Okay. You can ignore all the previous math, just stick with this point. And again, most certainly it would be on the exam, something related to this. Certainly it would be on the exam. Okay. So now let's look at this algorithm, by the way. This algorithm, where you calculate this gradient, okay, and take a step in the ascent direction. This is called reinforce. Okay, and it's used by algorithms like Gemini. Okay. Now, as I mentioned, the entire literature of reinforcement learning that is used in NLP or for large language models is essentially modification or improvement on top of this vanilla policy gradient. Okay, and we would do it for specific reasons. I'll explain why we are making those changes. Okay, but essentially this, if you understand this point, you are at a good starting point. So now let me come back here and let me try to write reinforce and tell you what are the good things of it, what are the bad things of it, what are the issues with it. Okay. So reinforce algorithm, what you will do is you will calculate expectation for certain trajectories which are induced by your policy network. You will calculate summation from t equal to 0 to t minus 1, the gradient of the log of the action at time t given state t, okay, and you will multiply it with the return. You take this, and then what you do is you say theta k plus 1 would be theta k plus some learning rate times, we call it gradient of j. This is the reinforced algorithm. Okay. What this will do is it will make the data where the return is high more likely, the data where the return is low less likely. Okay. Now the question is, how do we implement it in practice? Remember, we have an expectation here. Okay, so how did I suggest we approximate this expectation? Sample mean. Okay, so what we say is that the gradient of J, we will approximate it as summation from I equal to 1 to n gradient of log of phi theta for the ith trajectory action at t time, for the ith trajectory state at t time, for the ith trajectory the reward. Okay. I'm sorry, divided by the number of trajectories. Okay. In general, I am very bad at doing this division, writing the mean. I often miss it. The good thing is that it does not change the gradient direction. It just changes the gradient magnitude. So with learning rate, even if you make this mistake in coding, with learning rate, you can fix it. But again, don't make this mistake. Write 1 by n. Okay. I'm bad at it. I often miss it. Okay. So this is basically what we would call an estimator of the expectation. This is an estimator. This is a quantity which is not exactly the expectation, but we use it to estimate expectation. Okay. And we want two things in estimators. Number one, we want estimators to be unbiased. Unbiased means that if you take this estimator multiple times, average it, its value should be equal to the expectation. Number two, we want it to have low variance. Okay. If it does not have low variance, what would happen is that sometime it would, on average, it would be correct, but sometime it would be very wrong in the positive direction. Sometime it would be very wrong in the negative direction. Because of that, the training would be very unstable. And in fact, that's the one of the endemic issue in reinforcement learning algorithms is that the trainings are unstable because the estimators are very high variance. Okay. So now the entire set of tools that we would look at, their goal would be to make this estimator low variance. Okay. Issue with reinforce. Issues with reinforce. Number one, reinforces a high variance estimator. What happens because of this? Training is unstable. So what is the fix? Reduce the variance of the estimator. So let's see how we can reduce the variance of this estimator. Okay. So let me write the explicit expression for this quantity. Okay. So remember, we had fix my mistakes, guys. Don't let me change things without reason. Okay. So let me write the exact expression for this estimator. You have 1 by n, summation I equal to 1 to n, summation t to t minus 1, the gradient of the log of the action t for the ith trajectory, given state t for the ith trajectory, multiplied by the return for the ith trajectory. Okay. Let me write the expression for the return for ith trajectory in this expression. this would be 1 by n, summation I equal to 1 to n, summation t equal to 0 to t minus 1, gradient with respect to theta, log of pi theta, AIT, SIT. This thing is summation, let me call it t prime equal to 1 to t, beta power t minus 1, reward at time t prime, reward at t prime. This is the expression. Now I have a question for you. Let's say I am at time t. I am at current time t. Okay. I want to change the gradient of my policy number such that I can take an action which is better for optimizing my return. Can the action at time t change the reward that you received at time t minus 1, time t minus 2, time t minus 3? No. We are living in a causal world. We cannot change the past. Okay. So first thing I can fix is that I don't need to start from t equal to 1. Because what it's doing is that for each time, it's adding the reward of all the previous times and then doing the next thing. Okay. How can I fix it? The first thing I can do is I can say that using causality, I can simplify it to 1 by n, summation I equal to 1 to n, summation t equal to 0 to t minus 1, gradient with respect to theta, log of pi theta, AIT, SIT, summation t prime equal to t. Okay. T beta t prime minus 1 reward t prime. This is the first simplification that you did. Now, of course, this is an exact equality. Okay. What it means is that in expectation, the quantity, this quantity that you were considering from 1 to t minus 1, in expectation, this would zero out. Okay. But since we were adding it, we were carrying it out. So it was adding some additional variance to our data. Okay. Now I'm saying that I will remove it. This is a low variance estimator. Okay. This is the first improvement that we do in reinforce. Okay. The next improvement that we will do is that essentially what I'm currently doing is that I'm sampling. I have a nice figure for it. Let me find that. Essentially what I'm doing is that I'm sampling different trajectories. Okay. And I'm seeing the reward of different trajectories. So I have a green trajectory, I have a blue trajectory, and I have a dark blue trajectory. Okay. So the reward, the return on the green trajectory is the highest. Okay. The reward on the light blue trajectory is a bit lower. And the reward on the dark blue trajectory is the lowest. Now, most of the times in your setup, what you would do is you would set up reward between 0 and 1. Okay. So all of these would be positive quantities. Return for trajectory 1 would be positive. Return for trajectory 2 would be positive. Return for trajectory 3 would be positive. But for trajectory 1, it would be very large positive number. For trajectory 2, it would be a small positive number. And for trajectory 3, it would be further smaller number. Because what you are learning is an outward distribution, it would essentially do the same thing. It would make the probability of the first blue trajectory the highest, the second trajectory smaller, and the third trajectory smaller. But again, all of these are multiplied with positive numbers. Remember, I gave you an example. I said that imagine that for some data, the return is 1, and for some data, the return is -1. So -1, it becomes very clear how the probability will be. So can I recenter these G's? Can I make the returns such that the returns are centered around 0? Okay. Essentially, what I want to do in some sense is I want to take the mean of all of these returns and subtract it from each return so that some returns are positive, some returns are negative. Okay. This thing, if you have a constant thing added to all your data, if you remove it, it would decrease the variance. Okay. So let me see if I can do something in this regard. Yes. No. Why I only want to subtract the mean? Because I have an expression. I can only subtract the mean if I can show that on average, this does not make any change. Okay. For variance, I would have to prove the same thing. Now I have a proof for mean. At least I don't have a proof for variance here. Okay. So now if you look at my expressions, okay, if you look at my expressions, I started by writing some expression for my expected return. Okay, and I wrote the gradient of the expected. This quantity was the gradient of the expected return. Okay. Now I'm going to do some manipulation of this quantity to show that I can subtract a mean from G, and it would not change the result. Okay. So this is, remember, this is the gradient of the expected return. Let me write it on my current page. Okay. So it's basically integral of probability times return integrated over all the trajectories. Let me come here and let me write it. So basically, the gradient of the expected return this was gradient of integral of probability of a trajectory g of tau g tau. Okay. Now what I'm going to do is I'm going to, on the side, calculate an expression, gradient of probability of tau, some constant b d tau. I want to see what this quantity is. Okay. Let me solve for this quantity. Is it okay if I write integral gradient of, gradient of probability theta b d tau? Is it okay if I write it like this? B times gradient probability theta theta. Remember, b is a constant. Okay, so you can take it outside the integral. Okay, what is this quantity? What is this quantity? No. What is this quantity? Yeah, what is the integral of a distribution over all values? 1. Okay, so this quantity is b times gradient of 1. What is gradient of 1? 0. So this quantity is 0. Okay, which means that if I subtract it from my original expression, nothing will change because it's 0. Okay, so let me write this thing in a box. Okay, and let me continue my original expression. So it means that the gradient of the expected return, I can write it as gradient of theta g tau theta minus gradient of theta tau b theta. Why I can write it? Because this quantity is 0. So you can subtract 0 from an expression and nothing will change. And if you allow me to recollect terms as well, this would give me g tau minus b d tau. Okay. So I can subtract a constant from g and it would not change my gradient. Okay. Because in expectation it's 0. This quantity is 0. Okay. So I'll come here and I will say that this thing now I can write it. It's exactly equal to summation I equal to 1 to n, summation t equal to 0 to t minus 1, gradient theta log of pi theta AIT given SIT summation t prime equal to t v t prime minus 1 minus some b, and this b can depend on state, cannot depend on the policy. Okay. This thing, not exactly, but modifications of this are called actor-critic algorithms. Critic algorithms. So essentially, this part is the actor, okay, and this part is the critic. It tells it how good or bad your action is. Okay. So you might see some literature where actor-critic algorithms are used. Okay. Everybody is with me so far? Okay. Any questions? Okay. Okay. So if things are okay up till this point, let's take a short 10 minutes break because I don't want to launch another session of very advanced math without giving it. But just 10 minutes, okay? So let's reconvene at 50. Okay, let's complete this session.
Yes, I'm good. Asking about this, the big festivals. Because I talked with you said my name wasn't there. I remember I sent it to you. Ali called me saying my name wasn't there, so I had to talk to him again.
Can I? Can you This is the list that I gave him. Do you see your name in it?
Yes.
You see your name? Tell me what your GPA is and it will be easier.
No, it is not actually. Oh, here.
Okay, so he has your name.
Mm.
These are the names that I gave him this week. And I told him these are the people that I told him 3.6.
You might have missed it.
Yes, I told him 3.6 and above are the people that I'm recommending. But he will do the final selection. For example, say these people are these people
Gotcha.
who wanted something.
Okay.
Okay,
Thank you so much. I appreciate it.
What's the date of submitting the homework
I will announce it inshallah. Monday. I will put it.
on Monday? you put it? Yeah. So how many days maybe?
I'll give you more than enough time. It would be probably another 2-3 weeks. To submit, okay?
So the homework two is still
Yeah, it would be released tomorrow.
released tomorrow.
Yes. Okay, guys, let's resume. Okay, so we have just one last part for today's. We looked at German setup for reinforcement learning. We looked at the reinforced algorithm, which is used in Gemini. We looked at actor critic algorithms. Now I want to talk about transfusion policy optimization and proximal policy optimization, PPO algorithm, which is basically used in GPT based algorithms. They use proximal policy optimization technique to align their model. Okay, let's see what that is. Yeah. So essentially, what we want to do is when you are training a large language model, after you have passed through the first two stages of training, which is pre-training and supervised fine-tuning, you have your network, right? It can produce some text. Okay. But now what you want to do is you want to modify this network such that the new network has a higher reward than the old network. That's the purpose, right? Okay, so this, let's say you have done stage 1 and stage 2 of LLM training. It can produce some text. This is a fairly valid large language model. It will produce some text, and you will have some rewards for trajectories produced by this, right? You will have some GTOPs. Okay. Now what you want to do is you want to make some modification to this large language model's parameter such that the return that you get from the modified network, you want it to be higher than this network. So what you want is the return for the new network minus the return for the old network. You want this quantity to be greater than 0. If you can have an algorithm which can ensure this, then iteratively you will increase the performance of your model because you will get higher and higher rewards. Okay, and proximal policy network basically has this thing in mind. They want to solve for this. But for me to write the expression, I need to explain a couple of things to you guys. First is, what is a value function? Second is, what's a Q function? These are two things which I need to define because I need to define what an advantage is. And then once we have that, then we are set. Okay. So let's look at the value function. Okay. So if you are in, let's say you are playing chess. Okay. You can be in different states, like your pieces can be in different states. But if I show you a chessboard with certain pieces, certain moves, so let's say here, let's say you have king here, queen here, a knight here, and a couple of pawns here. This is your game, and then you have the other player has just a king and a couple of pawns. If I ask you who is likely to win from here, I think you guys would be able to say that red has a better chance of winning, right? So red player is in a better state than the blue player. So somehow can we measure what is the value of a state? Which state is better than another? We can do it, and this is measured in reinforcement learning by something called value function. Okay? So value function essentially is this. Value function says that given a state, if you follow a policy phi, the total expected return is value function. Okay, so essentially what value function is this. Value function is summation from of returns when you are like this expectation S naught is S, which means the starting state is S. Actions are sampled from policy network. What is the expected return? Okay, let me write it like this. Summation equal to 0 to T, reward. Okay, let me explain what this means. This means that you are in a state. From this state, I give you a policy. I tell you follow this policy. What would be the return that you would accumulate? This is value function for a state. Okay, everybody is with me? Everybody understand what value function is? Okay, would somebody mind saying to me what value function is? You want saying what value function is? Value function. So you start from a state S, okay? From this state, you follow a policy pi. The expected return that you collect, that's value function for state S, given the policy pi. Okay? Let me write it once more. Okay. I have to write this. Value function is for policy pi. So value function essentially would tell you how important or how valuable a state is given a certain policy. Okay, so I'll repeat it once more for Shahid Muhammad. Value function is a function which tells you what is the expected return when you start at a state and you follow a policy pi from that state. Once again, if I give you a state S and I tell you, I give you a policy and I tell you follow the policy pi from this state, you will collect some accumulated reward. That reward is value of the state subject to pi. So you see, I write value of S, but for a policy pi. And its expectation when your starting state is S, your action are sampled from your policy network, the cumulative discounted reward that you get. The mean of all the rewards when you start from a state S and you follow a policy pi. It's called a value function. Okay, it's super important in understanding these VPO type algorithms. Okay. There is another function which is called Q function. Q function subject to a policy takes in a state and an action, and it's the expected return when you start from state S0 is S and A0 is A, and then after that you follow your policy network. The reward that you get for S and A plus summation T equal to 1 to T, beta T, reward T. So exactly similar to value function, but value function, the state that you are in, you are following a policy from this state. In Q function, the first action that you take, it's not by a policy, you fix it. You define the first action. After that, you follow the policy. Okay? Everybody's with me? Okay? And typically, what you would see quite a lot in reinforcement learning is something called an advantage function, which depends on S and A, which is given as Q of S and A given 5 minus V of S given 5. Essentially, advantage function measures how much better an action is from a given state compared to the policy that you are following. If this thing is positive, then it means that from S, action A is better than your current policy. If this thing is negative, then it means from state A, action A, from state S, action A is worse than your current policy. Everybody is with me?
The value function here.
Yeah.
Control the action value.
Yes.
The value function higher. then the action will be minus. So my action will be wrong.
Yes, that's exactly what I'm saying. I'm saying that if this quantity is positive, it means that the action that you are taking is better than your policy. If this thing is negative, then it means that the action that you are taking is worse than your policy.
So, value, when it comes lower, it's gonna be better for me for the action.
This thing, if this is positive, yeah, you're right. So I'll explain. Let's do this. Let's say I want to go and find the door. Okay, this door. Let me stand here. Okay, and what my current policy is saying is that 50% of the time go right, 50% of the time go left. Okay, let's say that when I go right, the distance to the door is 10. When I go left, the distance to the door is 15. So what would be the average? The average is 12.5. Okay, in this case, distance is the loss. Okay, you will put a minus sign. So your reward is minus 12.5. Now let's say if I'm in, given this policy, I'm in this, so the V value is minus 12.5. Now I say, let me find the Q value. The Q value that I'm using is, I'm saying that at this stage, I'll move right. Okay, this is now a QSA. Okay, if I do that, of course, the distance is 10. So the reward is minus 10. Minus 10 minus 12.5 is 2.5, which means that if I take right step at this step, it's better than my policy, because policy is taking me 50% the right, 50%. That's basically the function of advantage function. Okay? This is what this advantage represents. Okay, everybody's with me? That's it. That's for PPO, that's the only concept that I want you guys to take with you. Now let me take a step back and let me explain why this is good. Okay. So what I want to do is, as I mentioned a little while before, some of you were not here, is that after you do stage 1 and stage 2 of your large language model training, you will have a policy network. This can produce language, right? And you will have some reward for it. Okay, you will get some reward. So let me call this theta old. Okay, because I will change it. I'll create a new one. Okay, and you will have some reward for this old network, old policy. Okay. Now what I want to do is I want to modify this policy network such that the new policy gives me a higher reward. Okay, let me denote this quantity by J. Okay, J is the expected return of the network. So I want J new theta new minus J theta old to be greater than 0. If this thing is greater than 0, then it means is that the modification that you are doing to your network is better, because you are getting better results. Everybody's with me? Now I'm going to write an expression. I'm hoping that you guys would agree with me on this. So J theta new minus J theta old. This quantity is summation from I equal to 0 to T, discount factor times advantage function for pi. Okay. ST and AT. Okay, and you have to do its expectation for all trajectories from theta mu. Write it more clearly. So expectation over all trajectory from pi mu. Okay. Summation T equal to 0 to T, a discount factor, advantage function, old S and A. Okay. Let me explain what this quantity is. Okay. This quantity says, if I want to find out how much better my new network is to my old network, I will sample some trajectories for my new network. So I'll ask my new network to produce an action in a state. Okay. I'll see what is the QSA value for this, and I will compare it to the V value of the old network. Okay, this is the advantage that I will have on the old network. And essentially what I'm saying is that just go and add up advantages at all time steps. This is the improvement that your new network will have on your old network in terms of return. Again, remember I gave this example where I said I have a QSA, which is go right, and I have a policy which is saying 50% go right, 50% go left. How much is QSA better than my old policy? It was just the difference of QSA minus the old policy, minus the value of the old policy. I'm doing the same thing. So I'm saying that sample a trajectory from the new policy, see at each action, state action pair, how better is this new policy from the old state value, and add them up. This will give you the overall improvement in return from this new policy. That's essentially what they do in PP. Okay, that's the objective. Essentially, this quantity you want to maximize. If you want, if you ensure that this is always positive, your job is done. You will continuously improve the return. Okay. So let me try to do it. How will I do it? How will I implement it? So after I train my large language models from stage 1 and stage 2, I'll call it by reference. I'll take my reference model. Okay. I will set the new model, view the reference model. I will sample some trajectories from it. Okay. Sampling from the new model, I sample some trajectories. Okay. And I will try to optimize this quantity. I'll take a step in the ascent direction. Okay. What this would mean is that the improvement in return would be positive. Once you change theta, you will have a new pi new. You will sample trajectories. You will do this again. You will have a new policy network. You will sample trajectories. You will do it again. New sample network, a new policy network, sample trajectories, and do it again. It's a very neat algorithm. The only issue is that you have to sample trajectories again and again and again and again. Okay. So essentially what would happen is that you would ask your network some questions. It would give you some answers. You will change the parameters of the network slightly. Then you will ask the questions again. Get the answers. It's too slow. So the trick that we want to do is somehow we want efficiency in terms of sampling. We don't want to sample every time again. Okay. And for this, we use a concept called importance sampling. And the idea of importance sampling is very simple. If I tell you to find the expected value of f of x, where x is sampled from p of x, and let's say somehow sampling from p of x is difficult. I can't do it. Okay. Will you guys allow me to do this? Will you allow me to multiply and divide by distribution f of x? Q of x. Okay. If you would allow me to do this, then I'm hoping that you will allow me to write it like this. And you will allow me to write this as expectation from q of x of p of x, q of x, and f of x. Okay. And this is exact equality. So the expectation of f of x under p is the same as expectation of p of x by q of x times f of x under q of x. Okay. Now you see why this is good? Because now rather than using trajectory from the new policy, I can use trajectories from the old policy. So I sample trajectories, then I reuse them multiple times. Okay, everybody's with me? That's basically the idea. That's the idea that they use in PPO. So they take this objective function and they write it as expectation of trajectory under pi old. Okay. And probability of trajectory new divided by probability of trajectory old times summation t equal to 0 to t minus 1 beta t advantage of pi old S and A. Okay. And there are some simplifications and there. I'm not going to go into its approximations, but basically this thing they simplify it to summation t equal to 0 to t minus 1 action at time t given state at time t divided by policy network old action at time t given state at time t beta t advantage of old. And that's essentially it. Let me just explain what this does. Remember, we want to maximize this quantity. So if advantage is high, okay, if advantage for a state action pair is high, we will try to increase the probability of that state action, that action for the new policy. We'll make it more likely. Okay. On the other hand, if advantage is low, we'll make the probability from the new network. That's it. That's PPO. Okay. PPO does some neat tricks with it, whereas they clip a few things here and there, but essentially that's the PPO algorithm. There's a minus sign here, but so this is the quantity that I just showed you. Okay. Pi theta is a new network. Pi theta old is an old network. Okay, A is the advantage. They use some clipping as well because they don't want to allow certain actions to affect the overall change in network too much. So the change that they want to make is small. They don't want to do very large jumps. And the reason for this is in LLM specifically is that what you have learned from English language is super important. Okay, alignment is a tiny part of it. So you don't want, based on the alignment, you don't want to change the full text, because if you do that, what would happen is that your network would produce just thank you, or happy, or good. It would learn to produce anything. So you want to restrict the changes. You want to make changes, but these changes are it's cherry on the top. You don't want to remove the full cake and just put cherry. Okay, so this is what this clip does. So clip says that if pi new by pi old is outside the bound of 1 minus epsilon or 1 plus epsilon, bound it in that interval. Don't let it go beyond that interval. Okay, you have another function which is for B function, because remember all of this is based on ability to predict what is the advantage. Okay, for advantage you should be able to tell what is the value of a current state given a policy. So they train a network for that as well. And this is basically just a supervised machine learning class. So they say that the value of a state should be equal to expected return for that state when you follow a policy. And last term is for entropy. Entropy is that they want to ensure a little bit of exploration into it. Okay. So for all practical purposes, you can ignore this. This is the PPO objective. This one is maximizing the return. This one is learning a value function. This one is putting some exploration, because endemic problem in reinforcement learning algorithm is exploration versus exploitation. Okay, so you might have seen that, like sometimes you might tell people like, hey, let's say, I'll give you an example. Let's say some of you are using GPT based chatbots. Okay, I can come and I can tell you like, hey, a DeepSeek is better, but you would be so used to it. It's not. So this works for me. This is exploitation. You have a policy, a current policy, which you believe is good, and you just rely on that. You don't search for anything new. Okay. Exploration is that every now and then you intentionally try something new. Maybe that is better. So this term introduce some exploration. ask you to try a few new things, maybe you'll find something better. Okay, don't rely on just current good policies. But again, for all practical purposes, don't focus on this, just focus on these two things. Okay, so that's PPO, and this, I apologize, it might have been a bit heavy, but this is essentially a full university course on reinforcement learning. But what can I do? I have to summarize it in one day. Okay. So the steps that we did, it's about half a course. Essentially, you started from policy, all the steps. But in my opinion, it's very simple to understand. Okay. Once you get a hold of, we will not use some very elegant math, very basic tools, expectations, simple tricks of logs, simple tricks of important samples, simple tricks of ratings, and that's it. Okay. So you will have the recording for this session. Try to go through it a couple of times. Okay, for sure, there will be some questions, some thinking questions. I'm not going to ask you to derive questions in the exam or enforcement level, just to see that we have the mental idea of what enforcement level is. Okay. Any questions? These are the new parameters. Okay. So this is the whole point, you see. So I'm preventing the new policy to change too much from the old policy, because I'm keeping it in this interval. I'm saying, okay, if it's beyond this interval, keep it in this interval. Don't go beyond. And you can, of course, do small learning rates. In certain cases, this is one version of PPO. In another version of PPO, you have explicit KL divergence on top of it. So you put KL divergence. You say that the KL divergence of, so you have your network from stage 1 and stage 2. Okay. So you have your LLM from stage 1 and stage 2. Okay, you call it PyRef. It's your reference network. Okay, it's giving you some action and some state. The network that you are fine-tuning, pi theta, A and S, you can put explicit KL divergence between these two. You will ask the new network to not move too far away from the old network. That's how we prevent catastrophic forgetting. Okay, and you will see a version of it tomorrow in DPO, direct preference optimization, where we explicitly put this in the objective function and then do some optimization. Okay. Any other questions? Any questions? Okay. Okay. So if there are no questions, we will end today's session. Once again, apologies. At the very least, you'll have an enjoyable iftar today because you'll be so mentally exhausted that the food will taste better. Okay. Anyways, so tomorrow we'll look a little bit at DPO and GRPO. GRPO is basically just once we do this, GRPO is just a simple extension of this, which DeepSeek is using. Okay. We would look at DPO. DPO is something which is important for people who don't have massive resources to train reward models. You don't need an explicit reward model for that. So we'll look into these topics a little bit detail tomorrow and have a summarization. And best of luck. Okay. Thank you very much, guys. I will upload the slides and the video.
This lecture was recorded.
It's recorded, yes. I will upload it. Thank you.
Thank you.